Hello everyone, hope you have a good day today. My name is David. Joining me, we have Jialing, Jonathan, Li Teng, and Wen Yang. We are from the National University of Singapore, and today we'll be sharing with you our project on the development of sustainable wastewater treatment plant with energy recovery through the use of biosorption and oxidation process at Singapore's PULAU Tekong Island. So here is the content for today. Next, PULAU Tekong is Singapore's second largest offshore island with a land area of 24.43 km². It is planned for future developments such as resort and residential areas. However, to prepare the island for the future development, it needs to tackle the challenges of treating its wastewater. As such, disposal of domestic wastewater effluent is a major problem that causes water pollution in some countries. Thus, when domestic wastewater is directly discharged into open water bodies, it may cause negative environmental impacts. Therefore, to tackle the domestic wastewater discharge, the PULAU Tekong Town Council has approached NUS for a proposal for the building of the wastewater treatment plant. In addition, the PULAU Tekong Town Council has given us limited space area of 0.0 km² to build our proposed wastewater treatment plant. The plant will have a buffer zone of 200 meters away from the residential and resort area. Based on Singapore's Environment Agency data, the typical wind direction in PULAU Tekong is blowing towards the northeast with a wind speed of 2 meters per second. Thus, with the good wind speed and direction, it is a good strategic location where it could prevent odors from the wastewater treatment plant to travel towards the resort or the residential area. Moving on, the wastewater influence shows here is taken from Singapore's average domestic wastewater discharge from residential area. Based on the data, the wastewater treatment plant needs to cater for high BOD and nitrogen domestic wastewater. Thus, if this untreated discharge water is directly discharged into the sea, it may cause eutrophication to occur. When eutrophication occurs, it reduces dissolved oxygen in the water source, thus affecting the marine ecosystem and wildlife. It may also cause detrimental health impacts towards the public. As such, to prevent the negative environmental impact, untreated domestic wastewater discharge has to be treated to the effluent standards that were set by Singapore. Moving on, other than meeting the discharge standards, there are a few challenges and criteria that we have to meet as well. Due to the proximity of the treatment plant, which is 200 meters away from the resort and limited space area of 0.01 km², the team faced a challenge of treating 100% of odor generated from the treatment plant and achieve a wastewater reduction of 90% to decrease the need of landfill. In most process treatment, energy consumption is one of the key factors which increase the operating cost. Therefore, it is important to minimize energy usage by recovering the available energy such as from biogas to save the cost of electricity needed and to promote lesser carbon footprint as compared to conventional treatment plants. Next, after considering the challenges faces, the team has came up with a treatment train and design layout which fulfills the requirements set by the PULAU Tekong Town Council. In our layout consideration, we have categorized the equipment used based on the environmental impacts, which includes the environmental risk, vibration, odor, heat, and sound. Equipment with a low impact, which indicated in green, will be placed around the perimeters of the plant, while high impact equipment, which indicated in red, will be placed in the middle of the plant to prevent any disturbance to the public or the environment. Lastly, the medium impact equipment, which indicated in yellow, will be placed in between the low and high impact. Next, the block flow diagram here shows our proposed treatment train, which consists of systems such as biosorption, oxidation, and biosolids. And now, I'll pass my time over to Jonathan, who will talk to you about each processes which we selected. Jonathan, please.
Thank you, David. So, given the additional challenges faced, the treatment processes were not just selected based on how efficient a process is at removing contaminants. We also considered odor control, energy efficiency, footprint, minimal waste production, and the ability for future expansions and cost savings. For preliminary treatment, we chose reciprocating bar screens as it's easy to maintain. We also implemented an equalization tank to ensure equalized flow and contaminant concentration so we can get consistent treatment performance downstream. For grid chambers, although aerated and vortex grid chambers are more compact, aerated requires more energy and vortex has inflexible operational capability. Therefore, horizontal grid chambers were chosen. For primary treatment, compared to a conventional primary sedimentation tank, biosorption process can produce much more waste sludge through adsorption of organics from the wastewater. The increased sludge production will allow for more biogas to be produced and can help reduce the plant's energy requirement. Utilizing activated sludge can also help significantly reduce organic loading, allowing downstream processes to be sized smaller and have a lower aeration requirement, henceforth resulting in much more energy savings to be made. This makes biosorption process to be much more sustainable than primary sedimentation tank. For secondary treatment, wetlands are aesthetically pleasing but cannot control odor and need large amounts of space. And membrane bioreactors are compact but costly to maintain. And for activated sludge process, although it is known for high energy demands, when it is coupled with biosorption process, it will require less energy in return. Therefore, activated sludge process was chosen. For disinfection, UV was ultimately chosen as chlorine disinfection has a much higher risk of producing disinfection byproducts, which could be harmful to aquatic and human life near the discharge area. To meet the requirement at discharge, cascade aeration was also chosen as it requires no energy and is simple to maintain. Overall, odor control was prioritized in all the processes chosen here, and with biosorption process, we are able to increase cost and energy savings and minimize footprint. For biosolids treatment selection, blending operations are necessary to ensure primary and secondary sludge are well mixed and to create a consistent sludge mixture. Furthermore, it also gives better off-bottom solids transport. Moving on, the gravity thickener scraper was selected due to its advantages which of such size. It is easy to operate, does not need chemicals, and needs minimal energy to operate. After the thickening process, we will also be using the anaerobic digester as it can meet EPA standards for Class A biosolids, and it can also produce biogas for energy recovery. Following that, Volley multi-disc screw press was used for dewatering because of its low environmental impacts, low energy consumption, and operating costs and land requirements. Furthermore, it can function automatically. Lastly, flash dryer was used as it can also meet EPA's Class A biosolid standards with a minimal footprint. Drying of solids can also make Class A biosolids take up less volume and weight, making storage and transport more convenient. In summary, with all biosolids processes covered in the center of the allocated land, biosolids treatment is effective in odor control, and the matrix also shows the processes having a balance between energy savings and land usage. Now I'll pass my time over to Wen-Yang who will talk about the treatment specifications.
Thank you, Jonathan. Now let's look at our design for the selected treatment processes. The reciprocating bar screens were designed to remove up to 30% of grit. Subsequently, horizontal grit chambers were designed to be capable of removing up to 95% of the remaining grit in the wastewater. The flow will then be equalized in the EQ tank, designed to be 13.4 meters in diameter and 5 meters in depth. Next, we'll move on to the biosorption stage. How biosorption works is that biosorption tank serves as a mixing tank, which mainly removes COD from wastewater through the use of activated sludge as the biosorbent to rapidly absorb and store organic matter on the active site. Absorbed sludge will be aided with secrete EPS from the activated sludge. The absorbed sludge is then settled in the primary clarifier to be recycled back for use in the biosorption tank. To ensure that the biosorption process continuously works, the RAS is aerated to oxidize excess absorbed organics to free up the sludge absorption site. In the biosorption tank, a short HRT of 27 minutes and a DO concentration of just 0.6 mg per liter was used to prevent excess oxidation of organics and allow the predominant removal methods of organics to be biosorption. With an SRT of 0.25 days and a biomass maintained at 2800 mg per liter, the design tank was calculated to have an FM ratio within the typical range of 2 to 10 and was capable of removing up to 51% of the influent BOD. To reactivate the adsorption site of the recycled sludge, the sludge aeration tank was designed to have a HRT of 15 minutes and the sludge will be re-aerated to a DO concentration of 2 mg per liter using 9 diffusers. Lastly, to maintain 2800 mg per liter of biomass in the biosorption tank, the clarifier was designed to be 17.7 meters in diameter with a 4.4 meter depth, and it will have a HRT of 2.34 hours and is capable of removing up to 79% of TSS from the biosorption tank effluent. Now I'll pass my time to Jialing to tell us more about the flowing processes. Jialing, please.
Thank you, Wenyang. So moving on, for the ASP, the first part will be the aeration tank, with each tank having dimensions of 19 to 13 to 6 meters, with a total of 4 units. Based on the SRT of 3.75 days and the MLSS concentration of 2800 milligrams per liter, we obtain a HRT of 4.98 hours and 51% of the flow will be recycled back from the FST. For the aeration requirements, we have selected a fine bubble diffuse air aeration system due to its ability of simultaneous mixing and ability to fulfill high oxygen demands. We will require 70 diffusers in each tank, and this system will help us to maintain a DO concentration of 2.5 milligrams per liter. Moving on to the clarification process, we will use 4 circular clarifiers with a peak overflow rate of 45.26 meter cube per meter squared per day. This allows for 2.48 hours of retention time, which is sufficient for good solid liquid separation. So moving on to disinfection and post-aeration, firstly, we have UV disinfection. So we designed it based on a dosage of 44 milliwatts seconds per cm square, allowing us to achieve a final coliform concentration of 50 CFU per 100 milliliters. To meet the discharge standards of 5 milligrams per liter for DO, the cascade aerators was designed to have 6 steps with 1.2 meters in height. Moving on to biosolids treatment, the main objective is to achieve good sludge quality so they can be used as fertilizers for agricultural purposes. So the sludge should be treated to class A, where they will be pathogen-free, resistant to vector attraction, and they can be applied to land without any restrictions. So for the processes, firstly, we have blending tanks. There will be 2 units each, which are 6 meters in diameter and 3.6 meters in depth. Gravity thickeners for 4 units are used where they are 10 meters in diameter and 5 meters deep. So these will be capable of achieving 93.5% of volume reduction for sludge. Moving on, to produce Class A biosolids, 4 units of digesters are used. So they are operating at 35 degrees Celsius and an SRT of 15 days. They will be able to achieve a VSS reduction rate of 52%. With this design, 2800 meter cube per day of biogas can be produced, which renders to 2 million kilowatt hours per year, and this translates to about 30% of energy savings annually. For dewatering, 2 units of dewaterers are used, and it can achieve 69% of volume reduction and 15% solid content in the sludge cake. For flash dryer, 2 units are also used, and they are used to further remove pathogens and reduce moisture content of the sludge. They are able to reduce sludge volume by 84%. So the wastewater from aerobic digestion, dewatering, and thermal drying operations will be sent back to the plant for treatment, while the processed sludge will be stored in sludge holding tanks. Subsequently, the sludge will then be used as fertilizers as they are treated to Class A biosolids. Finally, the wastewater and biosolid treatment processes can be summarized in this diagram over here. So the preliminary operations consist of the bar screen, grid chambers, and the EQ tank, while the biosorption tank and the primary clarifier will be used for primary treatment. The conventional ASP will be used for the oxidation process, while UV disinfection and cascade aeration will be used for tertiary treatment. For sludge processing to biosolids, it will undergo blending and thickening, then digested anaerobically. So the moisture content of the digestate will be removed through dewatering and drying operations. The final product, which is the biosolids, will be stored in a holding tank before it will be transported for land applications. To summarize for treatment performance, the discharge effluent into the sea are all within the discharge standards as shown in this diagram over here. As for the sludge production, 4,700 kilograms of sludge will be produced per day. Now I pass my time to Li Ting to discuss on our odor control measures, costs, and environmental assessments.
Thank you, Jialin. So in our odor control system, we'll focus on hydrogen sulfide and ammonia gas, as these are odor producing and could affect the public, wildlife, and workers in the treatment facility. So as seen from the table, most of the treatment processes produces odor. Thus, it will be enclosed with a cover. And we've further identified the various treatments that requires extra odor control, such as bar screens and equalization tank and the biosolids processing. As such, a wet scrubber will be used to control odor. So anaerobic digester does not go through odor control, as it will capture the biogas to generate electricity. So here are the operational parameters for odor control. So the wet scrubber uses sodium hypochlorite to oxidize the sulfides captured, and sodium hydroxide is used to convert hydrogen sulfide to sodium sulfide. And with that, the system is able to treat 11.9 kilograms per day of hydrogen sulfide. So next, for the OPEX of our treatment facility, we analyzed electricity, chemicals, disposal, and labor, and an estimate of $1.8 million is needed. However, with the utilization of biogas, we are able to achieve our target of 30% energy savings, and an approximate of $290,000 is saved, which brings the OPEX to around $1.5 million annually. Next, an impact assessment was done for the construction and operational phase of the treatment plant. And as you can see, the receptors are between moderate and critical region during the construction, as excavation works needs to be done, and it will affect the water and air quality, which negatively affects the workers' health and terrestrial and aquatic flora and fauna. Therefore, mitigating measures such as silt screens and relocation of endangered species will be done. Next, when the plant is fully operational, the receptors are generally at a minor region. This is because the water quality will be greatly improved and the likelihood of pollution will be reduced. So with heat-producing equipment strategically placed in the middle of the plant, which are away from the resorts and flora and fauna, we'll minimize the impacts on them. So here's a summary of our effluent and biosolids quality. So as seen here, our effluent parameters such as BOD, TSS, and ammonia nitrogen are well within the discharge standards and safe to discharge to the ocean. And our biosolids have undergone Class A standard processing and is safe to use as fertilizers. So in conclusion, our facility have a maximum treatment capacity of 19,000 meter cubes per day, and we're able to obtain a TSS removal of 98%, BOD of 97.5%, ammonia nitrogen removal of 96%, and a tree-log removal of fecal coliform. So with these percentage reductions, the effluent will meet the stringent discharge standards. In addition, the plant is environmentally sustainable as the treated Class A biosolids will be reused by horticulturalists as fertilizers, which helps to reach our zero waste goal. And mitigating measures will be put in place to ensure that humans and flora and fauna will not be affected during construction and operational phase of the facility. So the odor generated from the facility will be treated, which ensures that the air quality in the area will not be affected. So the energy recovered from the biogas will be used in the plant. As such, the plant is economically sustainable as the biogas is able to provide savings of $290,000. Thus, we've achieved our goal of energy savings of 30%. So all in all, our treatment facility using biosorption and oxidation process is able to meet stringent discharge standards and is economically and environmentally sustainable. So we'd like to take this opportunity to thank NUS and our faculty advisors, Professor Hu and Professor Ong, for their guidance. And with that, we'll end our presentation. Thank you.